In this lesson, we will quantify a prefetch timeliness window and compute how far ahead a prefetch should run for a streaming loop. The system has a last-level cache latency of 18 nanoseconds, main memory latency of 80 nanoseconds, and a 4 GHz core. The loop body costs 6 cycles per iteration. We will translate times to cycles and then to iterations and visualize the window where a prefetch arrives on time. First, the givens. The core frequency is 4 GHz, the last level cache service time is 18 nanoseconds, the DRAM service time is 80 nanoseconds, and the loop takes 6 cycles per iteration. A 4 GHz clock means 0.25 nanoseconds per cycle. 18 nanoseconds is 72 cycles, and 80 nanoseconds is 320 cycles. With 6 cycles per iteration, the loop advances one iteration every 1.5 nanoseconds. To hide a latency completely, a prefetch must arrive at least that many cycles before first use. Converting to loop iterations, last level cache needs 72 cycles, which is 12 iterations ahead. DRAM needs 320 cycles, which is 53.3 iterations, so we round up to 54 iterations to guarantee coverage. The prefetch timeliness window is the range where a prefetch both hides the full DRAM latency and is not so late that the load stalls. The latest just-in-time issue is 12 iterations before use. The earliest issue that still fully hides DRAM is 54 iterations before use. In time, the window width is 80-18, which is 62 nanoseconds or 248 cycles, which is about 41.3 iterations of slack. Let's see this graphically. This number line is lead distance in iterations. 0 means no lead. As we move right, we prefetch further ahead. We mark 12 iterations, the latest just in time from cache, and 54 iterations, the earliest that still hides DRAM. The shaded band between them is the timeliness window. Any prefetch issued in that band will hide the DRAM miss and arrive with enough time to be served from the last level cache. The width of the band is the slack, 62 nanoseconds, which equals 248 cycles, or about 41.3 loop iterations. We write this as an inequality for any acceptable lead distance d between 12 and 54 iterations ahead. If the loop streams one cache line per iteration, the lead distance in iterations equals the lead distance in cache lines. Therefore, any lead between 12 and 54 cache lines ahead will be timely. In practice, it is wise to choose a value somewhere in the middle of the window to absorb variance in queuing and interference. Here, a good starting recommendation is roughly 33 lines ahead. A quick statistical note: if we budget a 10% margin for timing variability, that is about 4 iterations. Centering the lead keeps us at least 4 iterations away from either boundary, which reduces the chance of arriving too early and being evicted, or too late and stalling. To summarize, at 4 GHz, the prefetch timeliness window for this loop spans 12 to 54 iterations ahead, which is 62 nanoseconds wide. Choosing a lead near the middle, about 33 lines ahead, for a 1 line per iteration stream, is a robust starting point. This balances timeliness with cache residency risk.